Yes, exactly. So I'm Peter. I'm from the Netherlands, and I have a slightly different background because I come from more of a artificial intelligence background. And it's been like 2 years since I started more like cybersecurity and side channel attacks, focusing on neural networks. So for the past 2 years, I've been doing this on various platforms. My main target is the GPU, of course. It's very timely. And so I want to give a brief introduction into why would you attack neural networks. And also I want to discuss how they're built up and how they relate to crypto when you attack them, so that you can, some people who may not be familiar with neural networks can understand that when you attack them, they are very similar to, crypto. But there are differences also. So our use case is at the edge, because usually attackers can have physical access, and we will need that for the attack. And especially nowadays, AI is everywhere. So also for your phone, even in medical devices, or yes, there is smart traffic control deployed nowadays. And there are some even scarier ones like drones, which I will show an example, and of course self-driving cars. So by extending on drones, so there are now drones equipped with AI that are very autonomous and can navigate even in circumstances which are not perfectly familiar to them. And so the IP and the neural networks that drive these is important to protect for example, for the military or companies that develop these. So there is, of course, financial incentive to protect these, but also these are just secrets that you don't want to leak. Another prime example is self-driving cars. I will show some example with concrete numbers of what goes into Tesla's autopilot. So it's a larger, complex combination of neural networks, which take, according to them, 70,000 GPU hours to train, which can go easily into the millions of dollars. But that's just the smallest part, actually, because collecting the data and also the R&D cost that goes into it is way more. And as an attacker, you wouldn't, even if you had access, for example, for the architecture, you wouldn't have access to the data set that Tesla has. But you have physical access to the car. So you might be able to reverse engineer a neural network weights. So there's a lot of money goes into it. So of course this is important for companies to protect. I think now we have established that it's important to protect these neural networks for companies, but also for militaries. There are other kinds of attacks, like membership inference, backdoor attacks. These are not side channel related, but the third main category, which is our category, is model extraction attacks, where you want to mimic or extract a functionally same model. And that's what our goal is in this work. And as I said, our use case is at the edge, mainly because we can have physical access, but also these devices are usually limited in their computing resources, and they have usually low latency requirements. And these are usually at odds with the countermeasures that you can use, because usually countermeasures also come at a performance cost. And that's why it's harder to protect these devices. So just briefly, I when I mean architecture, it's like how the structure of the neural network is built, how the layers and their order, and the weights are these internal parameters of the layers. Now, if you can get the architecture, that can be valuable, of course, but you don't extract functionally equivalent model without the weights. And so the architecture can be valuable, but you need the weights also to get functioning model. And when we compare it to crypto, it's roughly when you target the architecture, you want to reverse engineer. It's similar to reverse engineering what crypto algorithm runs on the target, which relates to operational leakage. And when we target the weights, it's roughly the same as targeting the secret key, which relates to data-dependent leakage mainly. And yeah, this is just it is the same, roughly the same setup. So usually we know the inputs and we want to get the secret key, or in our case, the secret weight. And yeah, so our research question was to whether GPUs are vulnerable to weight extraction, because it has been shown on other platforms like FPGAs and microcontrollers. But these are fundamentally easier targets. And after this, I want to talk about why the GPU is a bit more difficult to attack. And then we arrive at the CUDA programming model, which is built on a hierarchical model of grids of thread blocks. And what's important to us is that when these thread blocks are scheduled, the GPU further divides them into 32 threads, groups of 32 threads, also called warps. And these warps are the lowest execution units in the GPU. That's very relevant for side channel. So this is one of the GPU chips, the Maxwell 750 Ti. And you can see a lot of repeating blocks. These are the streaming multiprocessors. And we can just focus on one to illustrate how the GPU works. So even in one streaming multiprocessor, when it receives warps, there are 4 different processing units that can manage these warps. And the issue with this is that when warps are scheduled, managed, and in our attack we want the warps, a certain warp is scheduled at the same time in every measurement we make. Else we have misalignments in side channel, which degrades our attack. So the scheduling uncertainties regarding warps really make it difficult. So in our work, we targeted the NVIDIA Jetson Nano, which is an edge device that features the Tegra SoC with the Maxwell GPU. So the Maxwell is rather old architecture, but this device is still heavily used because it's cheaper and also does the job, so it's still heavily used. And so in our work, our target was to get the weights of CNNs, and so the target weights were 16 bits. And one other important assumption is that we assume that the architecture is known of the target, which is not trivial, but there has been quite some work also, like how to reverse engineer architectures on GPU as well. So that's why we assume that we know it. So some of the challenges with the GPU. We have almost 1 gigahertz clock frequency, which is really high. And the main issue comes with what we observed is the unstable clock, which again degrades our attack because it's harder to synchronize our measurements. And we need that synchronized measurements to be able to do the attack. And of course, we have lots of noise, not just from the tens of thousands GPU threads, but also like the whole system on chip and the OS that operates next to the GPU. And as I already mentioned, is the warp scheduling uncertainty. Yeah, these are things we cannot really control. This is just how the hardware works. And also, leakage modeling is very important when we do this attack. That's why, I will explain it in a couple of slides. But so just to show our methodology, the first phase is establishing leaking points and appropriate leakage model, which can be tricky. So for to do that, we just scan the whole package, just showed earlier, and also the nearby capacitors, and applied fixed versus random weight TVLA. Usually it's done with random inputs, but in this case, using random fixed versus random weight results in less false positives because the same input can be loaded at multiple times. And the second phase is we actually exploit the leakage using DPA. What's important here is that we go weight by weight in a kernel, but the attack can be parallelized, which I will talk about in more detail. In addition, we also wanted to see what happens if we have more, if you execute a smaller CNN or a larger CNN. By larger, I mean with more weights, and which results in more threads executed. So we have these two experiments to compare the amount of noise we get. So yeah, this is the surface scan we made to scan for the GPU clock frequency, and you can see that there are two hotspots, and the bottom right one is the one where we found multiple leaking spots for the weights, and also there are the nearby capacitors also leaked. This is also just a shot of our probe located between two capacitors. And this is a close-up. So there were multiple locations that allowed us to extract the weights. I can't really say which one is the best because our experiments were not really conclusive, but with the capacitors, it was easier to collect traces because there were more noise coming from the package, and there were some issues collecting traces over the package. I also want to mention that convolution can be implemented in multiple ways, and the preferred way on GPUs is by doing matrix multiplications or framing the problems matrix multiplications. But even there are also lots of special cases which you might encounter. For example, Vinograd convolution. And on this platform, or this GPU, with half precision, it was easy to, so you can dump the CUDA implementations and reverse engineer the binaries. And what we found is, well, it's straightforward, but there was like a kernel setup, the init block, then you had the convolutional block, and finally the bias and activation function calculation. So this was not surprising, but you still have to look at the implementations because there are differences between GPU architectures and the low-level instructions as well. So this is an example trace, and based on our reverse engineering, we can identify each part of the traces as the init, convolutional, and the activation function computations. If you go further in a bird's eye view, we can also just separating layers is very easy because there is a small downtime which you can clearly see between the layers as the amplitude goes near 0. And I want to also show the low-level leakage, so the low-level instructions that these implementation use. So these are the half fuse multiplied instructions. And what they do is they take 2 registers, 32-bit wide, and they operate on each half. And so what we have is that each register is updated with results from different channels, which also means with different weights. And this is relevant for the leakage modeling when we want to make our attack very efficient. So yeah, leakage modeling it's very important for the attack efficiency. There are multiple ways to attack the GPU. We can just focus on a single thread in a single warp or in a warp. This is the weakest one and the simplest one, but in this case we only have to guess 16 bits, so just one weight. As I said, this is the simplest one, but definitely not the most accurate leakage model. The second one would be to focus on multiple lanes in a warp, because usually the same weight is used in multiple threads at the same time. So we still have 16 bits of guessing, but yeah, this is a better leakage model. And the downside is that you have to reverse engineer the implementations more, and you need to know how the inputs are loaded exactly and which lanes operate on which inputs with the same weight. So this is more analysis. Then we can also just do, a single lane in a warp with 2 weights. And then, we have 32 bits to guess. And this is much better than the first one, but we stick to the first one in our experiments, but our goal is to make the attack more efficient. And there are many multiple leakage models that so even different warps can use the same weight at the same time, but this is harder to pull off. So this is just as a side note. So leakage detection. So this is the result of our leakage detection. And so you see a spike in a leakage in the convolutional block when we vary one weight. So that's good, but the leakage is just above the theoretical threshold. So this also shows that there is not a whole lot of leakage. But what we found is that different leakage models, so modeling the register states and the updates, so different leakage models worked to get the same weight. Also the bias, which shows a much higher leakage. This is probably due to ReLU, which is an activation function that by its nature leaks a lot because it zeroes out inputs, half of the inputs. So this is much more leaky as expected. And for some results, usually in our experiments we needed well, at most 20 million traces to get a single weight. But what we found is that comparing we didn't need more traces or more measurements for the larger architecture with more threads than what we needed for the smaller CNM, which was surprising. And also you can see in the plots that usually you would need a clear separation between the red and black lines. And we don't have that. So this also shows that what the leakage model that we use, the simplest one, is not the best one. Because there is not a high confidence in the correct candidate. I mean, it goes to p-rank 0, but still. And so we have a lot of leakage models or multiple leakage models that worked. And there was a huge variance in also the number of traces that we needed, because sometimes it was enough to collect 1 or 2 million traces to see convergence. But as I said, there were cases when we needed 20 million. So, and I think one of the last things I want to talk about is that compared to crypto, we have multiple weights, not just a single key, and even millions, at least millions usually. And while that's true, since DNNs are parallelizable, you can also parallelize the attack against them. So the differential power analysis, because lots of the computation in DNNs are independent, which also means that you can do the attack independently on the parameters. So in a convolution layer, you can do the attack independently on each kernel. So while you can do it independently, it's still expensive because you need more hardware, but theoretically it's possible. And just for reference, we implemented the attack in CUDA, and it took with our implementation, it takes 5 minutes for one weight, and roughly it would take like $50,000 to get a CNM with 5 million weights. So also our goal is to make the attack more efficient in the future, because this is not yet super efficient. And as for countermeasures, I think the standard countermeasures that are used for crypto, like masking, can be applied here as well. So, for example, we saw that in the binaries that the accumulator registers were initialized with zeros, and if they were initialized with a random number, then it would be much harder to get, for example, the weights. The other one is shuffling, which is also a standard one, where you actually randomize the order in subsequent executions of the computation. But this would just force an adversary to collect even more traces. As for EM containment, we are also looking into newer GPUs, and we saw that probably due to miniaturization, we see less leakage from the package. And we can also apply warp scheduling randomization intentionally, but I guess this would be this would incur a high cost on a logic or in silicon. So as I said, we are looking into newer GPUs also, and the trend is to use lower and lower precision for the weights, and which means that the complexity would be lower, but since these weights are packed into So let's say if you have 8 bits weight, 4 of them are packed in one register. So our leakage model would still need to be based around the 4 weights. And so in theory, it would be lower, but in practice, you would still end up with high complexity. And so overall, GPUs can be, the weights can be reverse engineered from GPUs. We found multiple ways or multiple leakage models to do so, but the attack is very expensive to do so, and but it can be done in like a feasible amount of time if someone has the resources to do that. And I think that's it. Well,
all right. Any questions? Well, I'm back.
Thanks. That was really interesting. I just was in crypto, you're usually using DPA. Of course, you're going after a secret key. It's 32 bytes in size. How large is your data target in this? I mean, what is like the total size of the neural net weight that you're trying to pull out of? Maybe in this
for each weight. So each weight is 16 bits.
Right.
And 16 bits floating point. But yeah, nowadays for inference, which is our target use case, this gets even lower. So 8 bits, and also it's getting now to 4 bits in newer GPUs, like it's supported by hardware also. So yeah, but in this work it's 16 bits. And yeah, that's also depending on the leakage model, it can be higher because did it answer your question? Sort of. So 16 bits for each weight.
For each weight, how many weights?
Well, in a target, so we had a toy example where we had just one kernel, and and we had the large network which had 5 million weights, but we only targeted the first 2 layers of that large CNN. So not all the weights, not all the 5 million, because also in the slide it was it costs roughly 50,000 euros to do the attack. So that's also one of our goals, to make it more efficient. But I still would think that it's not for an everyday attacker or average attacker. Still requires more.
All right. Anybody else? Going once. Going twice. All right. Thank you, Peter.
Thank you.
Appreciate it.